Well, thanks all for coming. Thanks all for the invitation for the seminar. I'm really glad to do my second seminar in this financial and computer analytics group seminars. So today I'm here to talk about my second experiment of my thesis. This is still ongoing research, so I'm happy for any feedback, necessarily in the paper, but also about the presentation. It's the first time I'm doing it, so feel free to correct me or to propose any new modifications or any ideas that I think would improve the work. So the title of the research is Generative Adversarial Networks, or GANs, for financial trading strategies, mainly focusing on fine-tuning of financial trading strategies and combination of financial trading strategies. So I'm Adriano Koshiyama. My co-supervisor is Nick Ferozi, and Philip Trelev is my main supervisor. This is the table of contents. Let's start. So I start talking a bit about GANs. So what are they? It's hype or hope. I'll just do a quick discussion about it. And then I will focus on the GANs that I've actually worked on, which is the conditional version of them, which is way more useful for time series, not only time series, but any data where there is some context or some autocorrelation structure embedded on them. I'm going to talk about what are they, similar applications, and one thing that I've developed in this work, which is maybe a bit novel, is how you select GANs. It's not very easy to select GANs in the more generative case, but in the conditional case, sometimes it's easy to select them. So, just a quick overview. Maybe some of you already know. So just introducing about the topic again. So, what are GANs? So GANs are basically two networks. So you have one of the networks, which is the discriminator. The other one is the generator. And they engage in a conversation or in a battle, which the generator tries to fool the discriminator, and the discriminator turns out to be fooled by the generator. And the main idea is you have real data. So you have a data set. Could be images, could be speeches, could be music, could be anything, or a time series. So you have a data set which is real. And you have the generator, which is usually takes in noise with some prior distribution. Could be just Gaussian noise. So the generator takes in Gaussian noise and creates some data, which is fake in principle. So you have real data and you have fake data. And the task of the discriminator is to classify whether this data is real or it is fakely generated. And they engage on this battle a sequence of times, and the main goal usually is the generator to be able to fool the discriminator completely, so the discriminator is able to 50% of the time say it's real data, or 50% of the time misses the fake data as well. So if you follow this economics or game theory literature, it's like kind of a minimax game. And the Nash equilibrium corresponds to a minima of this particular divergence, the Jensen-Shannon. And it's quite a tough job to train an unconditional GAN, in particular for images, because sometimes you don't know if they have converged or not converged yet. You never know if the samples are good or bad. So the unconstrained case to learn the unconditional distribution tends to be very complicated. So that's usually the game they play in several steps. So everything starts by real data and some generated data, which are fake. And this line over here is the decision boundary created by the discriminator. So in the beginning, the discriminator, in a way, is 50% of the time getting, let's say, the fake data and the real data, and 50% of the time is getting the fake data and the real data into different classes. But this is like starting from scratch. The first step is you train a discriminator, so the discriminator are able to perfectly separate real data from fake data, make the decision boundary perfect. Second step, you train the generator, so the generator is able to create data that now fools completely the discriminator, creates the new data on the decision boundary where it's real for the discriminator. And they do this over and over until it reaches this point where it's very difficult for the discriminator to separate both classes. And hopefully, maybe I have this image here. If you think about having, hopefully, the density of the real data, what's happening is the generator is trying to replicate, or doing a good job on replicating, the unconditional probability distribution of your data after a few steps. And there is different ways for you to learn this. You can use some density difference or density ratios. And every time that someone's come up with a new density difference or density ratio, you know what happens, comes up a new paper, and they create a new GAN. So you have a DC GAN, E GAN, B GAN, C GAN. So there is always a new GAN every year, and probably there'll be like 5 or 7 new on dips this year. So you see how it goes. But that's basically the GANs are. They hope or hype. There's a lot of hype, a lot of new recent research about the topic. They are very useful. There's a lot of criticism from people coming from some other areas like Gaussian mixture models and some people doing Gaussian processes. They say, oh, we are able to do that as well. But when they train their own models for images, for instance, they don't get the same quality as you would get with a GAN. We still don't know why, but that seems to be the way it is. This, for instance, is an interesting problem. I don't know if you know the celebrities. Some of you do know the celebrities. They in fact doesn't exist. They're not celebrities. They are fakely generated celebrities by a GAN. They look like celebrity, but they are not real. Just created ones. So they have the same archetypes of a celebrity, but they're not real. Same with art, and they have the cycle GAN, which you can pick a horse and transform it in a zebra by doing some cycling with the GANs. It's very fun. Most of the time they are doing this, they're doing images. Most of the research in GANs are images, some are in speech, some are in sound. I guess it's because of the inductive bias of the computer science department, which is usually computer vision and signal processing in a way. Not much on time series. Yeah, so let's talk about the ones I've been working on, which is the conditional ones. It's the same story, nothing changed. You just have to add a context. So instead of learning the unconditional probability density function, you learn the conditional version of that. And you add this variable here, it's the context. In our case, our conditional set is basically the lag information of a time series. If you are playing with spatial data, which I'm doing right now, it's quite interesting, you put in latitude and longitude as well, and also some information from the neighbors. So that's one thing that you can do. So in our case, the generator will give you an idea about the next value of the time series, given some P information backwards and some prior distribution of the noise. And you can train the same way as you do with the GANs.
You train it with prices or with the returns?
Sorry.
Do you train it with prices or with returns?
Returns. I think that's the main trick that you apply. Just putting context there. And because now the problem is way easier, you are able to select again along the training. And that's the main thing that makes it even more useful than the unconditional one. So finally, just a final mention. The conditional GANs, they inherit all the advantages of GANs. So some of the advantages are these ones. So data anonymization. So imagine you have a data set of real data. If you train a GAN for this data set, now the GAN replicates the data set. But all the data being generated by the GAN is not real. It's fake data. So now you have anonymized the real data because you can sample from the GAN and use the samples from the GAN to train anything you want. Of course, if the GAN did a good job. You can do novelty detection because you can use the discriminator to check whether this data comes from the real distribution or from the real distribution. Usually people just throw away the discriminator, but you can use it. And knowledge discovery, which is creating, I don't know, fake celebs and creating new kinds of music. You can just train again with classical music from Beethoven or Bach, and you can create something new that comes out of that. So a lot of things that you can. I don't know if it was in the media the other day, but I'm not sure if it was again. I think it was. There was this auction on Sotheby's or something like that about the first AI arts. So they sold like 500K. I guess that image was created by GAN. Not very sure about that, but here we go. Imagine potential about music and a lot of things. And you have some bonuses because now you're including conditional information. So you can do conditional inference because V can represent a current or expected market condition. And you can do some data augmentation. So the context could be a class with a very small portion of data, and you can augment only based on that particular class. Okay? So I don't know, for data augmentation, maybe I'm not using the right example here, but probably you have these huge data sets in which you just have like 5 or 10% of people with a certain disease, and you could augment that part of the data set, because that would be your context, would be that class and information from that class, instead of trying to augment the whole data set. Okay, cool. So if you look in the paper, there's probably a better description about this whole algorithm, but I'll try to do it right here in the presentation. So the way you train is the way things are trained usually with a traditional GAN. You do it for a number of epochs or training steps. You sample a mini batch of noise samples from noise prior, mini batch of examples. You update the discriminator first by sending stochastic gradient. Then you do it again, create more noise samples, and then you update the gradient by sending stochastic gradient. That's the funny thing these days is that everything is a stochastic gradient. So you just need to build the computational graph and just work out derivatives. It's so easy. You don't need even to talk about calculus 4 anymore to the students. Calculus 1 is enough most of the time. And that's what happens usually. So the first training step for S&P 500, first training step, that's what you get in terms of the GAN, the generator. So not good, but that's the random start. And then like after 1,000 epochs, starts to look like S&P 500. And then like 10,000 epochs, very strange. 15,000, kind of going back, but not as good. But as you can see, if you train for 50,000 epochs, 20,000 epochs, it doesn't matter much. You need to select them over the training.
So you train 500 series together, or one by one?
These are just samples.
Yeah, but
yeah. No, you just train one by one.
You train,
but you can train everything
So
together.
you have one real series.
Yes.
and you train another one.
Yes, yes.
And then you do for all the 500 with the 500 reals.
Yes.
And then you have the 500 trained,
Yes.
whatever they are.
Yes.
Each one you do 15,000 times or whatever.
Yeah, 20.
And the training set is what is 2,000 data set.
This I think is 100 samples that you can take from a single GAN.
No, I mean the number of entries you got daily data now is about a couple of thousand, I guess.
Yeah, 11 years, so it's probably
a couple of
2,000,
thousand,
3,000 data points.
Okay.
And you can do this, and it's usually the training is very quick. What takes time is the selection. Because for training for 20,000 epochs, 30,000 epochs, it's very quick. The problem is the selection. Then I go to the selection. We can do this because we are playing with time series, and we can do the same thing with spatial data. Maybe we cannot do the same thing with images. That's why I have this inception score and some other things are more complicated. So every number of training steps, you don't do this every training step because it's useless. So every number of training steps, you freeze the generator and the discriminator. So you freeze them, and you take samples from the generator, like I did here. You take samples from the generator every 10,000 epochs, for instance, and you compare the samples from the generator with the actual data. And you can compute some goodness of fit metric, RMSE. I discovered that I should have used a different one, which was you could just look into the autocorrelation and you can compare the autocorrelation functions of both. That will be a little bit better. But anyway. And then you just take a lot of samples and then you average your RMSE. And you do this along the training. And by the end of the training, 10,000 training steps, 20,000 training steps, by the end of this, and doing this process along, you return to the user the generator and the discriminator that minimizes this metric. Yeah.
So you don't reach any equilibrium, you just stop wherever it looks good.
Yes, yes, yes. Because it's also difficult to identify when they have reached the equilibrium. And there is some problems in
But
GANs.
this is not what they do in images, is it? I don't know. But that's a genuine question. I don't know.
Yeah.
I think they do reach.
They reach an equilibrium, but it's a very unstable one.
Okay.
And they have these different problems with training GANs. So one of them is called the mode collapse, which is something we can talk later on. Which is the GAN is able to replicate well one part of the distribution, one mode of the distribution, and the other
not
ones.
Everything.
But
But this fact that instead in time series you get that the GAMs essentially degenerates and goes very far from the right thing is typical of time series. It's not typical of other domains.
Yes, it's typical of time series.
Okay.
And we could potentially do this if we train 500 time series at the same time. We can compute similar loss. Maybe it's a bit would be more complicated. But that's the value of having unified one. Sorry.
Can you go back to the previous slide now? The point about the sample is that when you have images, you just let's assume that it's facial representation. With looking at the features, you can say that if the quality of something was acceptable or not, right? But what we see here is a sample of time series. How can you say that, for example, how can you say that the model is working? Like, how can you say that if the sample that is created here has a better quality than, I don't know, autoencoder model? Because here we don't have the luxury of actually being able to judge and justify.
I'll give you two reasons. One is the second part, which is this metric here, which do the selection step. That metric tells you this generator is better than the other generator along the training, because this generator is able to replicate the data better than the other one, and we can do this on time series specifically. That's one argument. And going back to the other thing you said about the images, is that I remember I tried to give I thought, okay, maybe this thing's not working, maybe it's just me who wants it to work. So I have this friend who's also doing PhD, and he was a banker for 10 years, and I showed him this sample over here. And he said to me, "Oh, this looks like S&P 500." I said, "Okay, fine." So it's not me. So it's kind of working. And the funny thing is, if you train using this whole process, you end up selecting not necessarily the same epoch, but somewhere in the neighborhood of this epoch.
About the measurement that you're using, that's very sensitive MRST. It's quite sensitive
Yes.
to the length of the lag of the model that you're using. So it's actually, I'm not very convinced that in authority it's actually the answer, because one thing is that with the number of data, sorry, I'm sure that you have thought about it, but the other thing is that with the number of data points that you have here, compared to the number of parameters that you're going to have, that's the size of the lag will become really crucial. And also, if I was in a real world, if I want to use the S&P sample, right? Okay, the top one, which kind of creates the edge of the surface, it looks like S&P. But if I'm training my trading machine, there is no guarantee that the sample that is created is going to be created from the top one. It can be the whole range. So I think it's a good idea of thinking about them one way, because I think this is the problem with the time series analysis.
Okay.
With voice, we can again have a way to measure it, but with this model,
But it's subjective with voice. It's very subjective, and you can use quantile GANs for generating certain quantiles of the distribution if you want that thing. So that's another thing that you can potentially use to solve this problem. So we just get a question.
So, maybe I didn't get it. The data you train on, is it index data or is it individual stocks?
These are individual stocks.
Because it looks like in 10,000 epochs you basically train to the average of
Yeah,
index.
it looks like.
It'd be interesting, I think, when you showed this, to show the actual distribution.
Yeah.
And yeah, especially the index.
And how many lags?
This was 252, so 1 year.
1 year.
1 year of lags.
Okay.
It's quite a long lag.
so the lag is from
I want to move on because I think
Yeah, no, in fact,
that I
yes,
have
please, in
different-
fact, that's what I want to
but,
say.
you
Move
just-
on and do answer at the end because
Yeah,
otherwise.
can I ask you can you just go ahead? Yeah.
Oh, I don't mind.
Yeah.
So maybe I missed this, but what is the context you're conditioning on?
Yes, is the past information, the time series. So you just take that.
But you don't have the data. It's just the past 200 or
Yes, yes,
Okay.
yes. So thinking back now, like you do these things and then you look back and say, yeah, I should have done better, and I should have used some recurrent neural nets. That's another discussion. So that's usually what happens when you look to the selection metrics. So if you compute the RMSE across 20,000 epochs, it's funny because it suddenly goes down and then it starts to goes up later on. And that's where it starts to diverge. Again, the discriminator, they try to play their own thing in a way. So you can potentially stop the training by here, or you can just leave it run to the end and get the generator from this stack. That's okay. And that's for you just to know that it doesn't make much difference how many samples you take. So it doesn't, just a bit more noisy. What matters more is the snapshot frequency. So how much time you're stopping the training and then you're just evaluating it. That's the most important. Just to give a highlights. So if you take the epoch 1000, it's a bit complicated, but if you look to the autocorrelation function and the partial autocorrelation function, there is a good match, or a great match, but there's a good match, and that's for 63 lags of them. I should have used this metric.
Yeah, but the autocorrelation of a 60 legs is pure noise.
It's completely spurious, yeah.
So you're just overfitting noise.
Yeah. And so, suppose there is some video. Oh. Not working. It's like GIF. This video here. Maybe I can show you later on. This is a GIF, so you can see the training happening and the distribution chain. It's very fun. That's the usually what people with GANs do. They do a GIF of the snapshots they take. If you don't do that, people complain with you. Where's the video about the training? So,
Okay. Cool.
So I'm gonna just
We
talk.
put it online.
Yeah, I'm gonna talk about the applications that I've done with. So fine tuning and combination. So just talk briefly. So there's this dilemma for the quant strats. So what training strategy I'm going to use, parameters, many lags to consider, data sources, performance metrics, and so on. And there's this broad research question, which is, can we set a framework that avoids backtest overfitting of a training strategy given dependent data in high-stakes scenario? That's kind of broad research question. Try maybe to solve a small bit of this broader research question. So you can make the problem stable, probably sit a bit more formal. So you have a finite set of examples. So you have a training data, draw from a certain probability distribution, Px. You have a set of hyperparameters, lambda, such as the number of neurons in a neural net, number of lags you have. So these are parameters that the user has to decide on. You have a training strategy with some parameters that you can identify given the data. So some are identifiable by the data, some are not straight away identifiable by the data, but you can use data to identify them later on. And you have this P&L function, or utility function U, to measure whether the performance of your training strategy is going to be in face of the new samples. And then our objective, ideally, is to do this optimization. So you want to maximize the expected utility or the expected P&L of your trading strategy, given the set of hyperparameters that you have. And then, just to make things more clear, you have these two approximations to the problem. So let me go back one slide. So this problem here, you first approximate by not having all the hyperparameters, but just a few of them. So instead of trying all the number of neurons, you just make a grid. That's what usually people do. And the second step is you don't have the expectation. So you take a mean. And you take a mean on a validation set, not in being able to source the data all the time from the real world. Just split the data, take the mean from it. And I guess you guys have noticed what I'm going for. It's like you can replace this validation set, or instead of throwing away this expectation, by putting a GAN here to replicate the P of X. So that's where the GAN comes in, this part. So the first approximation is because of the finite amount of computation, and the second approximation is because of the finite amount of data that you have. And if you can chart, this becomes this. So this would be the ideal world, and this would be the ideal hyperparameter. And then the first approximation basically discretize the function in a lot of points. So you just have now some points that you're trying. And the third one makes things uncertain. Because now you're in expectation, you have some sampling error, blah, blah, blah. It becomes now distribution. So that's the way people do things in practice. There's no way. So where GAN comes in is to be part of this model validation toolkit that data scientists and people in finance usually have. So in finance, you usually do some kind of rolling window or expanding window. So you train a model with some sample data, testing out of sample, do it again, out of sample, and so on. So that's one way. You can do non-IID bootstrap, like stationary bootstrap, circular bootstrap. You can do some other Markov CV and some other ways to do cross-validation. Or you can train again and take samples from again and use some samples for training, other samples for validation. That would be another way. So that will be the case. So you just replace P of x here for G of x. And when you generate the samples from the GAN, you just do one split. So hold on. And that's it. And I have some, I'm not going to show today the results about this part, but in the paper you can find it. I have some evidence that there is some benefits doing this too. So the another application that I'm going to show you, which is for combination.
The training validation, you do it historically.
Yes.
You're not mixing.
Yeah. And there's a holdout set that I leave out for comparing all the different approaches.
That's fine.
For the model validation one, I compare GANs with 7 different model validation techniques. You can look at the paper about that. For combination, I just compare with a single one, which is basically doing bagging that people usually do in machine learning. But, so what's the problem of combination? So you have a set of weak base learners, the very machine learning way of explaining. So you have a training strategies again here, but they're weak. They're like decision trees or linear regressions and so on. And they are generating lower expected performance. And you want to magnify them, empower them. So what you can do is you can build several of them and identify a combination of them such that that performance metric gets improved by the combination. And there's like different flavors in machine learning. So you can do variance reduction, which is called bagging. Usually, it's a technique called bagging. You can do sequential bias reduction. It's called boosting. Or you can do MSE reduction, which is stacking. And that's the bias variance trade-off. When you have a more complex model, you have low bias, but it tends to have high variance too. When you have a low complexity model, you tend to have high bias, but low variance. And the trade-off optimal would be to have a model which has low variance, low bias, and you can get the optimal model complexity. So any ensemble approach tries to surf this curve. In our case, we will surf the variance component of the curve. So we use a lot of low bias model, both high variance, so very deep decision trees or very large neural networks. It's a lot of very low bias, but very high variance models. And the idea would be to ensemble them so we can reduce their variance. So here's an example, so it makes things more clear. So you have a tree with max depth of 1. So here's the original function, this blue line. This is the original signal, as we call it. These data points here are signal and noise. So that's what we actually see in real life. So you have a blue is a signal. The blue dots are signal and noise. That's the actual data. And the red line you see here is a decision tree with just one level. So you just have one threshold. Okay? So that's has, and then if you can become more complex with depth 3, max depth of 7, and you can break down, because it's a simulated case, you can break down the 3 components, error, bias, variance, and noise. And what happens is so the ideal in this case would be a max depth of 3. You get the lowest error. But you can see if you use a max depth of 7, you get this level of variance, the bias, variance, decomposition. And the variance just kept increasing. Okay, that's this introductory example. And how to reduce the variance. You just try and select a conditional GAN, generate samples from the conditional GAN, train your weak models, and average them. Simple as that. So you have like a GANing. Instead of bagging, you are doing GANing. Try to call it for a name. how to do this thing. So the main mathematical device that I use is the variance reduction, and it's very similar to Markowitz. So Markowitz was right in the beginning. So imagine that you have a correlated sequence of variables. So you have all these models, and they are doing predictions based on a similar data set, so they are correlated. So if you take the variance, that becomes basically the variance of the individual models and the covariance between them. And you do the usual simplification, like the variance are similar, and the covariance is basically rho sigma square. Then you can write down the formula this way, and the variance of the ensemble is less or equal to the variance of the individual. And it goes down and down, depending on the size of the ensemble and the correlation between the members of the ensemble. So if you have a high diverse ensemble, very diverse ensemble, large ensemble, it tends to have a low variance when you put them together. So in our case, we argue that the conditional GAN is able to generate more diverse samples than Bootstrap, which is the main competitor. Hence, we can reduce rho better than Bootstrap. But the drawback, and I'm not going to hide this away, is that sometimes we may be unable to replicate well in data. And then we do samples that is not represents the true data, and end up with a bias component here in the formula. So that's why sometimes it works, sometimes it doesn't work. But the funny thing is, and I'm going to show a chart about that, is that when it doesn't work, usually Bootstrap works. And when Bootstrap doesn't work, cGAN works. So you can use both techniques and see which one I go. So that's usually another chart. So you take the tree of maximum depth 7, very low bias, high variance, and then you do the GANing, which is the, I don't know if it's a good name, but anyway, I'm trying to come up with a name for that. And you see the variance reducing as you increase the ensemble size. So that's just the experimental setup. I don't know how much time I still have. 5 minutes. So just try to do it quickly. So typical time series, I have 579 assets daily. Equities, rates, effects, 4,565 data points. The holdout scheme is one single split. So all the results I'm going to show you is in the test set, and or the holdout set, or the out of sample, depending on how you call it. And it's basically 5 years of holdout set. So it's quite a long holdout set. Mainly I opted for Sharpe ratio and Kalman ratio, got my results, because since I'm going to aggregate the results, it's difficult for you to aggregate average returns and volatility and so on. I prefer ratios, which tends to be better. And most of the time I'm reporting robust statistics like median, mean absolute deviation, quantiles, ranks, and I'm doing some Friedman and Holm to statistically compare the methods and so on. So you can find everything this. I did my homework, so it's very important. So this is usually the architecture. I try 3 architectures. For the current deep learning trend, I'm very shallow. So it's a mood layer perceptron. But sometimes it becomes big. So sometimes you have 500 neurons in the hidden layer of the mood layer perceptron, both for the discriminator and for the generator. And there's a lot of parameters. I'm not going to talk much about it. That's short time. So combinations of training strategies. I basically compare with stationary Bootstrap, which is the Bootstrap version for time series. And I use 2 training strategies, a shallow mood layer perceptron, but with a lot of neurons, and a regression tree, very deep as you can. So you have low bias and a lot of variance to results. Just some results. With did well for regression tree using cGAN, the largest one. We did not did so much well when the training strategy, the base learner was multi-layer perceptron. I tried to explain the reasons why in the paper, but that's kind of the summary. Still don't understand much. Sorry. Asset level, that's aggregate. It's difficult to understand what's going in the aggregate because it looks very similar. So you just chart things. So you visualize so you can see what's going on. And that's what I told you. When you have a chart of the Sharpe ratio for every asset, so every blue point here is an asset on the 5 years holdout set. When you plot the Sharpe ratio for the stationary bootstrap and the Sharpe ratio of the cGAN large, this is the chart you get. Apart from a few outliers, that's what you get. So what is happening here is, let's compare this part here. So get this quadrant here. So this part of the distribution, cGAN is doing a good job because it's a very large Sharpe ratio, and stationary bootstrap has a negative Sharpe ratio, so not good. And this happens again as well for stationary bootstrap. Do a good job, cGAN do a bad job. Sometimes both of them do a poor job, but sometimes of them they do both good job. But overall, if you compute the correlation of only this part is 0.3, 0.25, 0.3, it means that the two techniques are completely different in some aspects. They are correlated, but they are different in their own nature. And you can think about it because, bootstrap or stationary bootstrap is a model-free approach. And conditional GAN is a model-based approach. That's the name. And just to finish the presentation, if you just take SPX index and you apply stationary bootstrap and cGAN beats by a wide margin stationary bootstrap. So cGAN gets a Sharpe ratio of 500, of 1.0 when you increase the sample size to 500, and stationary bootstrap gets a Sharpe ratio of 0 when the sample size is 500. So stationary bootstrap doesn't work, cGAN does work for SPX. And there's other cases, similar things happen the other way around. So summary, full methodology on training selection of cGANs, how its step is used for strategy calibration, ensemble modeling. Future works, selection metrics for cGANs. So let's use advanced selection metrics and let's use recurrent neural nets. That's the takeaway. I think in combination of training strategies, which was the results I showed you, a good future works would be you can combine both strategies. Because since they are lowly correlated, if you combine both, a bit of a samples from one, a bit of samples from the other one, they outperform. And I did some analysis on that, and I can see some interesting results. Last slide. In fine-tuning, we can do some cGANs for stress testing. That's an idea from Nick. It's quite a good thing to do later. There's a lot of extensions that you can do, which is predicting multiple steps ahead, putting all the assets together, considering other architectures like other GANs, or ensemble of GANs. And you can do some adversarial training of trainers. That's just my funding agency. Also thank the Turing Institute for providing me some infrastructure to work on. And also, of course, for UCL for everything. And the full paper you can find on this link. Thank you all very much.
Can I ask two questions? First, why cGANs and not autoencoders, which looks like to me more logical for this purpose?
Well, that's a good question. I think the GANs, their main advantage would be that you're trying to, because you're using